Välkomna till Kungliga Vetenskapsakademin och den här presskonferensen då vi ska presentera årets Nobelpris i fysik. Welcome to the Royal Swedish Academy of Sciences and this press conference where we will present this year's Nobel Prize in Physics. We will keep to our tradition and start in Swedish and then continue the presentation in English. And you are of course welcome to ask questions later on in either language. Jag heter Hans Ellegren och är ständig sekreterare här på Kungliga Vetenskapsakademin. På min ena sida sitter professor Olle Eriksson, ordförande för Nobelkommittén i fysik. Och på andra sidan professor Göran Johansson, ledamot av Nobelkommittén för fysik och sakkunnig inom ämnet. My name is Hans Ellegren. I'm Secretary General of the Royal Swedish Academy of Sciences. To my right is Professor Olle Eriksson, Chair of the Nobel Committee for Physics. And to my left, Professor Göran Johansson, member of the Nobel Committee for Physics and one of the experts in this field. Årets pris handlar om att möta kvantmekaniken på ny skala. This year's prize is about encountering quantum mechanics on a new scale. Kungliga Vetenskapsakademin har idag beslutat att utdela 2025 års Nobelpris i fysik till John Clarke, University of California at Berkeley, USA, Michel Devoret, Yale University och University of California at Santa Barbara, USA, och John Martinis, University of California, Santa Barbara, USA, för upptäckten av makroskopisk kvantmekanisk tunnling och energikvantisering i en elektrisk krets. The Royal Swedish Academy of Sciences has today decided to award the 2025 Nobel Prize in Physics to John Clarke, University of California at Berkeley, USA, Michel Devoret, Yale University and University of California at Santa Barbara, USA, and John Martinis, University of California at Santa Barbara, USA, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. Professor Eriksson will now give us a short summary of the prize. Please.
This year we celebrate the centennial anniversary of the discovery of quantum mechanics and the seminal publication of Werner von Heisenberg. This is a theory of the microcosmos, that of atoms and electrons, and there is no advanced technology used today that does not rely on quantum mechanics and quantum physics. Examples are easy to find in the room: mobile phones, computers, cameras, and the fiber optic cables that connect our world. Quantum mechanics stands on several pillars, most prominently the energy quantization and the quantum mechanical tunneling phenomenon. This year's Nobel laureates have shown experimentally in studies published in the mid-1980s that quantum mechanical effects are found in new vistas outside of the realm of the microcosmos, hence embracing macroscopic objects.
Thank you, Olle. And Professor Johansson, can you give us a more in-depth presentation of this year's prize?
Yes, thank you. So, this year's prize is about quantum mechanical tunneling. This is a quantum mechanical effect that was discovered soon after Erwin Schrödinger published his famous wave equation in 1926, almost exactly 100 years ago. Soon after it was published, solutions were discovered where a particle could penetrate a classically impenetrable barrier. So to the left here, you see that exemplified by a wall, and the little boy throwing a classical ball onto the wall. It always bounces back. However, quantum mechanical particles can sometimes appear on the other side of this classically impenetrable wall, and it is as if it dug a small tunnel through the barrier. Hence the name. Soon after tunneling was discovered, it was also discovered that it's not only an astonishing theoretical prediction, it also has practical implications in the subatomic world. So to the left, you see a big nuclei, lots of protons and neutrons, and so-called alpha decay of this nuclei can be explained by the fact that the alpha particle, 2 neutrons and 2 protons, is bound, it's part and bound to the nucleus by a barrier. And classically, it would never ever leave the nucleus. However, due to quantum mechanical tunneling, it can appear outside of the nucleus, and thus you have radioactive decay. And the fact that it's quantum mechanical tells that it's a completely random process. And also by calculating the width and the height of the barrier, you can calculate the average waiting time for this decay or the half-life. So, we understand that quantum mechanical tunneling is important in the subatomic world. However, can we observe larger systems that tunnel? This was a question raised by Nobel laureate Anthony Leggett in 1978. He suggested that it should be possible to observe something called macroscopic quantum tunneling in a superconducting circuit. So how should we understand this? Well, in the upper picture here, you see a normal conductor. In the normal conductor, the electrons are very individual. They are fermions, and they are very easily distracted. So if you push a current through this conductor, the electrons are easily distracted, and there is resistance. Thus, you always get the voltage across this conductor. In the second picture, you see how a superconductor works. Here, the electrons take each other 2 and 2 by the hand, and then it's much harder to distract them. So then they can lead a current without any resistance at all, so there is current without any voltage, a supercurrent. In the lower picture, you see another example. You see also an illustration of how this works. It's actually so that all of the Cooper pairs lose their individuality altogether, and they all condense into one macroscopic state. So it's one Cooper pair condensate, which is determined by one macroscopic wave function or a superconducting order parameter. And you see there is a small gap between the two conductors in the lower picture, and that's a so-called Josephson junction. So in 1962, Brian Josephson predicted that you can, even if there is a small weak link or a gap in the conductor, you can still have a supercurrent. And he derived simple equations for how the current and the voltage in this junction relates to the macroscopic wave function on the two sides of the weak link. And from his description, you can do the following. If you push a current through the Josephson junction, it can then appear in 2 different states, one without the voltage and one with a measurable voltage. And the switching between the 0 voltage state and the state with the voltage is, there is a barrier in between. And by detecting how this switching occurs between the 0 voltage state to the voltage state, this is how our 3 laureates managed to prove that there is macroscopic quantum tunneling. So, to the left, you see an illustration of macroscopic quantum tunneling. So, our 3 laureates positioned, they push a current through the junction, And it was in a state so that it should not classically be able to switch. And yet, it switches from the 0 voltage state to the state with the voltage. Although classically you see that it cannot switch. And if you're a physicist, you might realize that the smoking gun evidence for this macroscopic quantum tunneling are when the black dots here deviate from the diagonal line. That's where macroscopic quantum tunneling dominates. So the 3 laureates, so this breakthrough experiment was performed in 1985 at Berkeley, and the group leader, John Clarke, had long experience of working with Josephson junctions. John Martinis was his senior PhD student at the time, and Michel Devoret was a postdoc coming from Saclay outside of Paris, with experience from low-temperature physics, but not with Josephson junctions, molecular solids. So this trio did not only do this breakthrough experiment, they also did another breakthrough experiment the same year. So the name quantum physics comes from the fact that atoms absorb and emit energy in packages, so-called quanta. And by irradiating the Josephson junction with microwaves, they could verify that this macroscopic object absorbs energy in a quantized way. So there are quantized energy levels. So, yes, I just want to mention also that in this system of the Josephson junction, there are billions of Cooper pairs. So it's really a macroscopic object in that sense. Okay, so this might sound a little bit abstract. However, this is a sketch of this experimental setup coming from John Martinis' PhD thesis. So you see the scale bar to the right, 1 centimeter, and there you see the silicon chip with superconducting wires, and the Josephson junction is exactly where the 2 wires meet. You apply the current to the left at the power connector, and then you measure the voltage at the same place. And when you radiate with microwaves, you do that in the microwave contact on top. Then you also see there's a copper tubing and copper powder inside, and that's a newly developed filter for this experiment that isolates the Josephson junction extremely well from the environment, which you need because these quantum effects are very sensitive to interaction with the environment. And I think to make it even a little bit less abstract, I also want to show you a modern quantum chip. So the silicon chip is the square in the middle here. And there are superconductors on top. And then there are 9 artificial atoms on this chip. And you can see them with your naked eye. So the 3 laureates has established, so the picture illustrates how they have taken quantum tunneling and quantum physics from the subatomic world onto electric chip. So now we had 40 years of lots of groups in the world exploring quantum physics on a chip, engineering artificial atoms, exploring quantum physics in regimes which are hard to get to with natural atoms, because you can engineer these artificial atoms. You can also couple the superconducting atoms to mechanical oscillators, and then you probe quantum properties of mechanical oscillators. And you may also have heard that this is one of the platforms where you can develop a quantum computer. Thank you.
Thank you, Göran. Do we have Professor Clarke with us on the phone?
Yes, you do.
Good morning, Professor Clarke, and congratulations to the Nobel Prize in Physics.
Thank you so much.
Was this a surprise to you?
So, to put it mildly, it was a surprise of my life. Okay. And I'm very sorry my two colleagues are not with us. But...
I'm sitting here in this beautiful session hall of the Royal Swedish Academy of Sciences at the press conference with many interested journalists here, both from the national and the international press. Are you ready to take some questions from them?
Yes.
SVT?
I have to congratulate you on the award, of course. My first thought was that it's quite mind-boggling, your discoveries. I was wondering, did it occur to you at the time that that you managed to prove there is microscopic quantum tunneling, that it might be the grounds for a Nobel Prize in physics?
I think that had not occurred to us in any way.
Oh, pardon, I didn't get that.
I think that it had not. We had not realized in any way that this might be the basis of a Nobel Prize.
Do you remember the specific breakthrough and how it what happened at the time?
Well, Michel Devoret and John Martinis are brilliant people. I worked very closely with them for at least a year on this and other topics. And the first thing I would like to say is that this discovery would never have happened without the two of them. I was in principle the leader of the group, of course, but their contributions are just overwhelming.
Okay, one question there, please.
Hi, Professor Clarke. This is Yiwei from the Chinese Media Intellectual. First, congratulations, and I would like to know your feelings now and where you are now. And the second question is, what do you think your research has left the open questions for the next generation of physicists? Thank you.
Well, first of all, my feelings are that I'm completely stunned, of course. It had never occurred to me in any way that this might be the basis of a Nobel Prize. And I'm sorry, what was your second question?
My second question is, what open questions does your discovery leave for the next generation of physicists?
Well, I think that, as already been suggested, this is something that does lead to the further development of, or the development of, sorry, I'm losing my words, of the quantum computer. I mean, many people are working on quantum computing, and I think that, I think that it is recognized that our discovery is in many ways the basis of this.
Yes, please.
Thank you. Bogun Radajewski from the Polish television. Congratulations, Professor. I wanted to ask you because, well, everyone in this room has a smartphone, and we have cameras that use memory chips that are actually based on the effects that you were studying. I wanted to ask you, did you predict when you made your discoveries that they are going to have such a widespread practical applications? And what do you think is going to be the next step in that regard?
It certainly had not occurred to us in any way that this discovery would have such a significant impact. and we were buried in understanding the physics and the calculations that went into this. And it was very much following up on this brilliant work by Tony Leggett, who of course also subsequently won the Nobel Prize. Also, I would like to say that I knew and still do know Brian Josephson very well. He and I were colleagues as graduate students together in Cambridge all those years ago. And I recognized that he was much more brilliant than I was. And I think that he and Tony will also be very thrilled that, along with Michel Devoret and John Martinis, we won the Nobel Prize. Mm-hmm. I'm not sure that I answered your question, but...
More questions? Yes, please.
Thank you. Congratulations, Professor Clarke. My name is Yan Nanzhu from Mises Salon in China. And my question is, quantum phenomena are universal. So where exactly is the boundary between the classical and quantum worlds? Thank you.
Well, I think that the real difference is that the quantum world depends on quantum mechanics, which, as someone commented earlier in this discussion, quantum mechanics was discovered many years ago now by Schrödinger, almost 100 years ago. And that's the underlying basis. The thing is that classical physics doesn't depend on quantum mechanics. But it's really this discovery by Schrödinger almost a century ago that is the sort of underlying basis of all of this work and of quantum mechanics.
Mm-hmm.
I'm Anneli Megner-Arn from Swedish TV4. Congratulations. I wonder what connections you see between the quantum computers and your discovery.
Well, I think that our discovery in some ways is the basis of quantum computing. Exactly where all this fits in is not at this moment entirely clear to me, but I think that this is one of the excuse me a second. I think that I think that the basis of quantum computing relies to quite an extent on our discovery. But our discovery, as I said, also depends on many other people like Brian Josephson and Tony Leggett.
Yes, please, there, in the back.
Congratulations, Mr. Clarke. Constantine from AP. Could you tell us how your discovery is used by average consumer today? Thank you.
Well, as people have pointed out, I mean, many straightforward applications are things like the cell phone. And I'm speaking on my cell phone, and I suspect that you are too. And that one of the underlying reasons that the cell phone works is because of all this work. And of course other applications too, but I think that the most common one, I mean, almost everyone has a cell phone in the modern world.
One last question.
Congratulations. Professor Clarke. I have one question. Is that I'm also an experimentalist, and now we say this superconducting qubits and the neutral atoms and trapped ions are both good candidates for supercomputing in the future. Which one you think is most strength in the future?
Sorry, could you repeat those again, please?
So my question is that for the moment we know that for superconducting qubits and neutral atoms, like cold atoms, and also ion trap, so they also show a very good candidate for the future superconductor. So which one do you think that is most probably for the future that we will use?
I'm sorry, I don't quite understand that. I mean, you talked about qubits and neutral atoms, and what exactly are you asking?
Maybe we need to take that question afterwards.
Okay, yes.
I think this was the last question for you, Professor Clarke. Thank you, and once again, our warmest congratulations.
Thank you. Thank you so much.
We look forward to meeting you in Stockholm in December for the Nobel Prize ceremony.
Yes, well, I look forward to being there too.
Yeah. Bye-bye, and congratulations again.
Good. Thank you. Thank you. Goodbye now.
Okay, so let's move on to more questions about the physics prize and the research involved, or if you want to ask the committee something about their work. And again, you can ask either in English or in Swedish. Yes, please.
Thank you. I'm Yanliang Guo, and I'm also an experimentalist in cold atoms. And then my question, I have two questions. So the first question is that we know theorists is the ones that foresee the future, and experimentalists that is realize this system and then to change our daily life. And then when evaluating Nobel-worthy contributions, how does the committee balance the value of this original theoretical breakthroughs and that delicate experiments that realize these theories in the lab? And second question is that when evaluating Nobel-worthy contributions, does the committee also take into account or consider the potential influence for the future science and applications, or it is just focused on the past achievement? Thank you.
Göran?
So, yeah, I mean, the last question first, of course, we can only regard what's been achieved so far. So we can only give a prize for something that has been done already. I mean, both deep theoretical insights are of course very important, but experimental discoveries are, I mean, lies at the heart of physics. So they are both extremely important. And we should also remember that this should be for the greatest benefit of mankind. So we definitely do consider what's the impact of these discoveries.
Olle, do you want to add something?
Yes, so as Professor Johansson says, the will of Alfred Nobel states for the betterment of mankind and the field of physics. And so this, of course, could be something that is very practical, but it could also be something that tells us where we are in cosmos, you know, anything on cosmology and black holes. And it's important, I think, to remember the quantum mechanics has basically three founding fathers. It's Heisenberg, Schrödinger, and Paul Dirac. And Paul Dirac was awarded the Nobel Prize in 1933. And he was asked at the award ceremony then by someone like you, what is the use of your discovery? And he says, I don't think there's any use of that at all. And he was asked again, but maybe in the future. And he says, no, I don't think so, not even in the future. And so this genius of a man, for once he was wrong, because as I said a few minutes ago, there's no technology that we use today that does not rely on their discoveries. And so the important thing here is that science always advances our society. So even if we don't know something for tomorrow, goodness will always come.
I think it's time to stop there. If you have further questions, you can ask committee members after this press conference. Thank you for your interest, and we hope to see you here again tomorrow when we will announce this year's prize in chemistry. Thank you.